So hi, today we will make a brief introduction to three-phase inverters, and we will talk about six-step control techniques. So three-phase inverters, they are commonly used in industry, actually in many other applications as well. So one of the main applications are variable frequency drives. So to drive three-phase electrical machines, as you have seen, like a variety of different rated applications. And also they are used in photovoltaic inverters, wind turbines, back-to-back converters, and so on. So most of the three-phase inverters are made using that kind of modules. So if you look carefully, you can see the equivalent circuit here. Actually, they are made of 6 transistors, and you can see the DC terminals. Probably these are the DC terminals, and these are the three-phase output, where you connect your motor or where you connect to the grid, etc. And smaller pins are for controls or for measurements. So the usual schematic is really similar to single phase full bridge inverter. So what we have is, remember, this is a leg or half bridge. So this is a leg. So we make two of those things, so you can have a single phase inverter. So in three-phase inverter, we just add another one. So we have 1, 2, 3 legs. So at each leg we have 2 transistors and their anti-parallel diodes as well. So you get the phase connections through the midpoints of upper and lower transistors, and you have the DC link or DC source connected to that one. Okay, so again, we have the same rules, so you don't close the top and bottom switches at the same time, so you don't want to short circuit those legs. So those are complementary, and actually practical cases there are some dead time between those turn on instances as well. So then point 0 is not needed, but it is shown for simplicity in calculations we will use in analysis, but you don't have that midpoint. You can have just a single capacitor, DC link capacitor, and you will have just 3 cables going to your motor or your grid. Okay, so then current can flow both from your switch or through the anti-parallel diodes. Anti-parallel diodes are important because if you have some kind of inductive load, so when you turn off those switches, they need some path to flow. We will discuss those things in detail. And actually there are like many PWM techniques. So we have seen a simple one for single phase, but there are many different techniques for three-phase or many-phase inverters. So the first one that we will discuss today is the square wave, or in short, a six-step PWM. And another really common one is the sinusoidal PWM, SPWM. And there are some hysteresis bank control techniques. Space vector SVPWM is quite different from the sinusoidal PWM, but they are also used commonly in motor drive systems, vector control systems, that kind of things, and third harmonic injection, etc. And again, like there are many different techniques with different advantages, disadvantages. So I would like to give you some basic understanding of those PWMs as an introduction. So first, let's start with the six-step inverter. So six-step inverter or technique, or PWM technique, it's commonly used in BLDC motor drives. BLDCs, remember, short for brushless DC motors, and that kind of motors are became really popular with all drones or small electronics, gimbal systems, I don't know, robotic applications, position control applications, and that kind of motors. I mean, even if they are called brushless DC motors, they are actually permanent magnet synchronous kind of machines. So, and therefore here you see like 1, 2, 3 cables going out to your motor, and as a input you have a DC coming in, and you have the motor drive here working, and you have all the input and output connections, and here you see your transistors, proper MOSFETs, and they are turning on off and off your switches. So let's have a look at the operation characteristics. So here you have again one leg, second leg, third leg, so you have 6 transistors in total, and here you have the physical connections of your BLDC motor. So again, the first phase is connected here, and second phase connected to there, and third phase is connected to here. Okay, so you can all connect your motors. So again, you can either turn on or off, and actually when you turn on the top transistor, that voltage potential is connected to your let's say this is VDC. So either you can connect that phase terminal to VDC or 0 volts. Okay, so you have different combinations. So it's in 6-step inverter, again there are some other techniques for that one, but for the simplest one, you have each switch has like 50% duty ratio, and each leg has a phase difference of 120 degrees, and one switching action takes place every 60 degrees. So you have one position. Okay, I will show the graphs. So you have one position, one configuration. For example, for that one, the first orange phase is at 0 volts. Okay, then the green phase is at positive voltage, and the other one is at negative voltage. Okay, so you have that configuration kept for 60 degrees, then the switching stage changes and so on. So those kind of switching are not really that fast. You are not switching at like at kilohertz or 100 kilohertz. You are switching more or less at the fundamental frequency. So for that switching techniques, the switching losses can be minimized, or you can choose slower and therefore cheaper MOSFETs. Okay, so let's have a look at the configuration here. So again, that motor, usually they are Y connected. Let me get rid of myself, and you have all those connections here, and you have the neutral connection. It is terminated at the motor side. These are the phases of the motor, but that one is not carried back to here. So let's have a look at one switching state. For example, you turn on, okay, so you turn on that one. Okay, so S1 is connected to DC, and let's have a look at what happens if we just connect E and C, the other two lower end terminals connected. So this one that is connected, that one are connected. So if you just follow that thing, okay, so let me try to draw it here. That switching configuration is equivalent to applying some phase voltages. I am giving some VDC, okay, and again, if here is shown with the inductances, but you can say like R, and again, if this is I, and if they are sharing it equally, it will be I over 2, and that will be I over 2 as well. Okay, so the potential difference, it will not be shared equally. It will not be like VDC over 2, but instead it will be VDC over 3 and 2 VDC over 3. Okay, so that may be one configuration. So what you are doing, we will talk about the sequence as well, but let's say then you are turning on that one, for example, then B phase is on, and then the other legs are closed for B and A. So now, I mean, at first, I mean, if you think about the phasors and MMFs, you know, motor DQ axis, as you have seen. So for example, in this one, phase A current is I, okay, and the other currents for phase B and C are like minus 1 over 2 and minus 1 over 2. Let's say this is A phase, B phase, C phase. So you can calculate, you can generate a MMF of 3 over 2 something something. Okay, then your MMF will be aligned with phase A in the first configuration that I showed. Then you can align it with phase B. I mean, here, for example, now phase B is carrying some positive current, but A and C phases are carrying negative half currents. So in that configuration, our MMF is aligned with phase B. You can align it phase C, and also you can align it with the inverses. For example, at the first configuration, let me again. So if you draw it for circuit, that one, and that one. So now current is coming from A, and they are carrying like minus I over 2 from phase B and C. But the complementary of that switching state can be something like that. So what you can do is you can close here as well, but then you can turn on like 2 top switches from phase B and C. So now phase B and C are carrying I over 2, and phase C is carrying minus I. So in that configuration, our MMF is not aligned with A, but it is 180 with A. So again, you know, if you just think about all the AC motors, I'm not getting into detail, but you have, let's say, a permanent magnet rotor. So once you align it with A, it will try to come to that position. Then you can move 60 degrees to minus C on my figure. That will come there. Then you align it with B, it will rotate like that. So minus A, then C, minus B. So if you just do that, you know, according to the rotor's position, you can rotate the rotor, you know, at specific positions, and you know that is the 6-step inverter or square wave inverter, and it's called 6-step because there are like 6 different switching states. And again, if it doesn't have to drive a motor, but if it is driving a motor, that 6 switching states correspond to 6 different rotor positions or MMF positions. Okay, so again, you know, if you just look at the sequence, so at first let's start at that instant. So here, if I just go back, clean that part. Okay, again, the numbering can seem quite unconventional, but it is just to make easier the others numbering easy. So here S1 is there, S2 is here, so S3 there, S4, S5, S5. So it is like actually that kind of cross numbering system, and you just start from S1, for example, S1 on, then S2 on, then S6 is on. Okay, so that corresponds to so S1 is on, S2 is on, means on, then S6 is on. Okay, so from here. Okay, so that was our first state, like the one I drove here. A phase is connected to VDC, B and C are connected to 0 volts or the negative polarity of our VDC. Okay, so the nice thing is, so now I am getting it into the next state. Okay, I was here, and next state, so S1 is still on, so there is no switching state change. S2 is still on, but I am turning off, okay, that instant I am turning off S6, but I am turning on S3. So in other words, so that one is same, that one same, but that one is just inverted. So just I am changing at every position change, I am just changing the position of only one transistor leg. So instead of S6, now I have the S3. So now I have A and B are connected to VDC. Okay, so A and B are carrying I over 2. Okay, I over 2, and C is carrying minus I. So in the first position, MMF or equivalent, phasor direction was like that. So now it is aligned with minus C because C is carrying minus I current, so it comes to here, right? So then I'm just changing one state, then I move one step more, which is 60 degrees later on. So now I'm at that position. So now S2 is still same, S3 is still same. So I'm just making one change, turning off S1 and turning on S4. So that corresponds to, so now that one is turned off and that one is turned on. So now let's have a look at that one. So now the only phase connected to the positive polarity is phase B. Okay, so phase B is carrying I, and phase C and phase A are connected in parallel, so they are carrying minus I over 2, minus I over 2 with respect to their positive polarities. So then it is aligned. Again, my diagram is not that nice. Now it is aligned with, draw it again. Okay, so it was aligned here at first. And here, and it was there, then you will be here, and it will all go if you just do it yourself. So you will see, that kind of sequence will create kind of a rotating MFF, and every 6 degrees, every 60 degrees, sorry, what is happening is the positions that two legs are kept constant, and the other leg just changes from top switch to low switch or vice versa. Okay, so that means you are not constantly turning on and off your switches, so that reduces your switching losses. So let's have a look at the voltage characteristics. If you have a look at the line to line voltage, okay, for line to line voltage, actually you have three positions. Again, it is like a 3-level voltage source. Inverter, for example, between phase line to lines of A and B, VAB, either A can be connected to VDC and B can be connected to 0, which results in VDC voltage, or B can be connected to VDC and A can be connected to 0, which results in minus VDC, or they can be either connected to 0 or they can be either connected both to VDC, which will result in 0 voltage at line to line. So you have three positions, and actually if you follow that sequence, what you will see at the line to line voltages is you will have 110, 20 degrees for VDC, and then 60 degrees off, and 120 degrees minus VDC, and then 60 degrees 0. You have that kind of square voltage at line to line voltage. Okay, and actually if you just draw the same line to line voltages for different phases, what you will see, okay, it is the same waveform, but every phase is like, this is 120 degrees shifted with respect to the previous one, and that one is 120 degrees shifted. So it is like a three-phase voltage. And again, you can get, of course, we will discuss those things. You can have the fundamental component of that waveform. Drawing, the magnitude will not be 4/3 because it's not like 180 on positive and 180 negative square waveform. There are some zero periods, but of course you can calculate the Fourier series. We will discuss that one. So I think in my browser version, you can see the animation of that one working. And again, I suggest you to watch that video. And there are some like driver circuits for BLDC motors, and depending on the rotor position, because in the synchronous machines you want to keep the load angle at some specific position, and again you want to fire those transistor instances with respect to rotor position. So it doesn't have to be, okay, so it doesn't have to be like constant frequency, constant magnitude, but the frequency can be changed according to if you want to accelerate your motor, decelerate your motor, so on. The frequency can be changing, but assume if it is running at constant speed, then like every switching instant will take place at 60 degrees. Okay, so this was the sequence, and this was the line-to-line voltages. And again, draw it here again, at every switching state, two of your phases will be connected, something like that. I mean, it can be A, B, C. So there are like 6 different combinations. And if that neutral point is floating, and if this is your VDC, then the sharing of, if you want to calculate the actual phase voltages, will not be like VDC over 2, right? It will be either VDC over 3 or 2 VDC over 3. And actually, if you draw that thing for equivalent phase voltages, what you will see is there's actually like 1 VDC over 3, 2 VDC over 3, another step, then minus VDC over 3, and minus 2 VDC over 3. So you have that kind of configuration. And again, you can get like the fundamental components, and you can calculate the harmonics. So let's do that. First, for the line-to-line voltages. And again, I just leave it for you as an exercise to derive the Fourier coefficients. But actually, if you look closely, and if you have, okay, the fundamental can be calculated by multiplying it with a sinusoid and getting the integral like we did in the first semester for a square wave. And actually, if you take the third harmonic, okay, then you need to multiply that signal with a harmonic 3 times of the frequency of that. Okay, so you have some positive here, positive, negative, so it is negative. So this is 0, and it's multiplied, so that is 0. So that part and that part, they will cancel each other, and at the end of the day, you don't have any third order harmonics in that configuration. So even if it looks like a square, you have a eliminated the third order harmonics. And actually I think we discussed that with some similar diode rectifiers in the first semester. So remember the current waveform of a three-phase diode rectifier. It looks like, you know, that one. So for that one we didn't have third harmonics, and since it is an AC signal, we don't have even harmonics as well. So the only harmonics we have is first the fundamental, then we don't have second because there's no even harmonics, we don't have third harmonic, we don't have the fourth harmonic, but we have the fifth, seventh, then we don't have the ninth harmonic because it's a multiple of a third harmonic, then we have 11 and 13, and actually they are in the form of 6k plus minus 1. Okay, and for the fundamental component, yes, if you put n is equal to 1, you have 4 over pi VDC coming through here, but we have that cosine term. Okay, cosine 1 times pi over 6, so it is cosine 30 degrees. So there's another square root 3 over 2 component. So it is kind of different, okay, kind of different from a normal square wave in which we have 4 over pi as the magnitude of the fundamental component. So the fundamental component has reduced, and also we got rid of the third order harmonics. Anyway, so if you calculate the RMS values, so 4 over pi VDC times square root 3 over 2, again I leave you as an exercise to derive that expression, the previous expression, and if you divide it by 1 over square root 2, what you are going to find is around 0.8, actually 0.78 VDC. Okay, so that means if you have a DC link of 100 volts, okay, if you have a DC link of 100 volts, you will be able to generate a line-to-line voltage of 78 volts RMS. Okay, and again for other harmonics, they are really similar to square wave. So for the fifth order harmonic, the magnitude is 1 over 5th of the fundamental. For the seventh harmonic, it's 1 over 7th. So on, it's directly as in the square wave. Okay, so here you see the distribution of line-to-line harmonics, and like neutral point, again it is floating, and we have, you know, that kind of waveform, and actually every switching at, you know, 60 degrees makes the phase voltages changing at 60 degrees. So that is again why it is called a, you know, 6-step inverter. Okay, so for the line to neutral harmonics, you have that configuration. It is slightly more complex expression, 1 over n, 2 over 3 pi. Again, you know, you are not responsible for that one, but actually that term can be simplified, and it is 1 over n, 2 over pi VDC. Again, for the line to neutral voltages, it is the same harmonics, you know, no third order harmonics, and actually you can calculate the peak. So peak is 1 over n, 2 over p VDC, and you can also calculate, I think I didn't put here, but you can also calculate the RMS voltages. So I have an exercise to solve in class later on. Okay, thank you.